Welcome to the April program meeting. By the way, this image, I was going to leave it dark because we're talking about dark matter, but this is allegedly a representation of dark matter. So Dr. Eric Cotner is going to give us a presentation on dark matter, observational evidence, and experimental searches for it. I always talk to the calendar. It's not quite as full as last month's, but this Friday we have Stars at West Sycamore and a presentation event that Kathy will talk about later. So I'm hoping people will come early, bring your telescopes as early as 6 o'clock and come for the presentation festivities in case there are pictures and we can have telescopes in the background and so forth. TDS Public Star Party on Saturday, then our normal types of things, Kumeyaay Campground on the first Friday, Oak Oasis and a Public Star Party. The program meeting next month will be on Zoom again, and Steve Flanders and I are going to make a presentation about Palomar Observatory science and history in advance of the tours resuming on June 10th. West Sycamore, a charter school, KQ, and the Sycamore Canyon on the other side are also coming up in May. I like to pull out some astronomy news that maybe people haven't seen. This was on the Caltech website. Another gravitational wave observatory, this time LIGO in India, has been approved. And this is going to be designed with Caltech and MIT help to be very similar to the two LIGOs that are in the United States up in Washington and Louisiana. And in addition to now these three LIGOs, there is also a Virgo in Italy and a CAGRA in Japan. And with all of these instruments operating at the same time, they expect to get the accuracy of a fix on the source of a gravitational wave down to 10 square degrees. If you remember with the very first detection, just with the two LIGOs in the United States, they were looking at huge error bars, and there was ambiguity about which side of the fix that they were actually seeing. I like to show something from the ASIG. This time it's Mark again, and he posted a picture of the tadpole taken at TDS. He used a 5-inch refractor with I think an older ASI 1600 camera, and he used filters to come up with the SHO combination. So, you know, let's go out and try to get the tadpole. This really looks pretty good. I'm going to turn the meeting over to Kathy for 5 or 10 minutes from the International Dark Sky Association to talk about the dark sky and the presentation this Friday. Kathy, it's yours.
Thank you, Ken. Hi, my name is Kathy Hansel. I'm serving as the Vice President of the San Diego County chapter of the International Dark Sky Association, and we don't have a president. So if anyone's interested, let me know. The International Dark Sky Association, also known as the IDA, was founded in 1988 by David Crawford, a professional astronomer, and Tim Hunter, a physician and amateur astronomer. Through education, outreach, and advocacy, the San Diego County chapter raises awareness about light pollution and promotes responsible lighting in order to reduce glare, light trespass, and sky glow. Our membership includes high school students, retirees, people from all professions and all walks of life. I'm not an astronomer, but I've always loved gazing up in the moon and the stars in the sky. And I started researching light pollution and joined the IDA after noticing the new 4000K daylight white streetlights, which hurt my eyes and turned my sun visor into a streetlight visor when I drive at night. And also because of a lot of light trespass into my home and yard from neighbors who don't understand that it's kind of not, you know, it's a little inconsiderate. Neighbors wouldn't spray their hose or aim their sprinkler system into their neighbors' windows and yards. But when we do it with light, people just don't seem to get that that's, you know, not okay. Here in San Diego, in the city, we have lighting ordinance that was written a long time ago. I think it was last updated or even implemented in 1997. It's definitely in time for an update, and we'll be pursuing that. And one really fantastic thing that's happened is because of International Dark Sky Week, and thank you for that beautiful image, Ken, we asked the city of San Diego and the county of San Diego to issue proclamations. So this week was actually International Dark Sky Week in the county of San Diego and also in the city of San Diego. The county proclamation was presented, as it was mentioned, out at Santa Isabel Nature Center last weekend, had a really good turnout. That was celebrating International Dark Sky Week, which is an IDA event, but also Doug Solacey took the lead on that. Doug's an IDA member and also founder of the Julian Dark Sky Network, which was responsible for getting Julian to become an international dark sky community. So he took the lead on that one, and I'm taking the lead on this event that's happening in San Diego. We hope to have a good turnout. I tried my best, sent out media invites, promoted, reached out via email to high school not high school students, but high school science teachers, a little bit of social media. I'm not a pro at that, but we'll see what happens. The other thing is in the proclamation for the city, I don't think it made it in the county one either. I provided this large draft and they really whittled it down. One of the statements I provided to the city and also to the county was, whereas local astronomers from the San Diego Astronomy Association partner with San Diego Parks and Rec Department and also county parks in the other one, to provide free telescope viewing star parties in urban parks to share the wonders of the cosmos and provide local children, youth, and adults with a connection to the natural nighttime environment. Now, unfortunately, that statement got cut, but we'll try again next year and see if we can't get that in. I personally want to thank those of you who have partnered with me when I've come out with my little light pollution booth and glommed onto your star parties. And I sincerely hope that nobody feels that I kind of hijacked this West Sycamore event. I really was just coming with my booth to celebrate Dark Sky Week. And then this proclamation kind of blew the lid off it. But there has been so much light pollution in the news. If the new book, Darkness Manifesto, there was articles in the New York Times, in the New Yorker, touting light pollution. One of them was titled, "Is Artificial Light Poisoning Our Planet?" That was kind of an attention-getting, title for an article. So originally, this started out, astronomers noticed we need to kind of cut the light down a little bit. And what has happened is we're learning that there are health impacts as well. I'm a breast cancer survivor, and I'm committed to raising awareness about the potential harmful health impacts of exposure to too much artificial light, especially blue light, which tends more to stop the production of melatonin, therefore changing all these physiological processes in our body, resulting in all kinds of health effects. The other way I'm tackling this is the angle on energy waste. Wasted money and energy shining light into the sky, and that also contributes to greenhouse gas emissions. So I'm going to be touting that to the city, that it's not just so we can see stars. We're trying to move to electric cars. That's going to be using a lot of energy on the grid at night. Well, let's turn off some of those outdoor lights. Let's bring back the stars and put some of that energy to use more wisely, charging cars. And then lights out for birds. Not only do we have this partnership with the San Diego Astronomy Association, at a national level, IDA and Audubon have formed a strategic partnership to protect the night sky for both people and birds. So we've reached out to San Diego Audubon. We also have Palomar Audubon and Buena Vista Audubon up in Oceanside, and we're partnering with them doing light pollution tables or booths at their events and giving talks. And we're hoping to work with them to launch a lights out campaign, lights out for birds. My opinion is I don't care why they're dimming the lights and why they're turning them off and aiming them down, just as long as we do it. Because just like cigarette smoke was just everywhere, you couldn't escape it. And it took decades before we learned that we have a right to breathe clean air that's, that my coworker isn't smoking and blowing it in my face, which used to happen in the office. But, I lost my train of thought. Oh, for it's like cigarette smoke, this light is just everywhere. We just can't escape it. So I really, again, hope that the awareness. Oh, here's another one. Guess what? National Pollinator Week is happening in June. Guess what? Artificial light is killing off pollinators, our monarch butterflies. I read an article, University of Cincinnati. If you like monarch butterflies that migrate, that magnificent journey they take, maybe you should turn off your porch light. It can affect their circadian, their navigational abilities. So the harms we're finding is so widespread. Yes, we want to bring back the stars, but there's so many other angles, we're taking at this. So I think that's all I have to say. I don't know if there's time for questions or if we need to continue on with the scheduled presentation.
We've got something from Dennis. Dennis said, Kathy, I promoted IDA and showed 50 people last night our San Diego County light pollution at Agua Caliente County Park last night. 1/3 of the sky is trashed from the southwest to the northwest by Tecate, Mexico, Tijuana, San Diego, Escondido, Oceanside, Fallbrook. Boy, there are a lot of perps here. Temecula, Riverside, and in the east by El Centro. It is so sad to see that glow all night.
Yeah, Dr. Quimby from Mount Laguna did a great video, and I'm hoping to leverage that, showing from Mount Laguna Observatory the sky glow in the distance and labeling where it was coming from. At Dennis, one of my best friends, Amy Lint, her daughter Mita was at that trip. So thank you for doing that. So that's awesome.
And Scott Cardell has one from Palomar that he took while he was there, but we can take a new one and identify the light sources.
Oh yeah, any of those. We'll be updating our San Diego County IDA website. We don't have much content out there, but we actually have had 195 hits on that site so far in April from just the little promotion that we've done. So we're hoping to put some more content out there. And then I do hope we can expand our membership and have our booths at more of the star parties. I just think that that's a great way to connect with people, and they see the telescopes and then they learn about light pollution. Even though I understand that you talk about it too, but having the pamphlet and showing them, I have a really good light, bad light diorama that I'll bring tomorrow. And yeah, hopefully it's a hit. And I hope our city leaders really start to take this to heart, that it is something really important and we have so much to gain and really nothing to lose but a bunch of glare. I'm all for it.
That's pretty well. Listen, Kathy, thanks for breathing some life into the IDA, because we in SDAA strongly endorse what you're doing, and we certainly are the benefactors from your renewed effort. So thank you.
Thank you. Thanks everyone for having me. I really appreciate it.
Okay, my last slide is an introduction. If they'll let me do it, yes. Okay, tonight, as I said, the topic is dark matter, observational evidence, and experimental searches. Dr. Eric Cotner, he does have a PhD in physics and with some distinctions, but he's also a data scientist. And I'm not going to talk too much about this slide because his first slide that I've seen is going to be something about his bona fides, but look at the last one. His hobbies are cooking, diving, programming, and there he is with his diving rig. So without further ado, let me turn the meeting over to Dr. Eric Cotner, and I will pull this down somehow. Stop sharing.
Thank you, Ken. Appreciate the introduction. Let me share my screen here. You all see my screen?
Yes. Yes.
All right, great. So yeah, again, thank you for inviting me to come and give a talk here today. So given that the purpose of the club, I suppose, is astronomy, I figured I'd better give a talk on observational evidence for dark matter. So I'll go through some of that. So like Ken said, I have a very brief introduction for myself here, just to kind of convince you that I have some credentials to speak about dark matter. So basically, educational background, I have a bachelor's and a PhD in physics. I graduated with my PhD about 4 years ago. I specialized in astroparticle physics. So it's kind of a combination of particle physics and astrophysics and cosmology. I would consider myself more of a particle theorist than an astrophysicist or an astronomer. I'm also quite interested in learning more about astronomy myself, hence why I kind of reached out to the group. So yeah, hoping to learn some stuff myself. But yeah, so I got my PhD in 2019, and then after that, I decided I'd been doing physics for a while. Maybe it's time to try something new. So I made a career change into data science, and machine learning was kind of the hot thing, and still is to some degree. So I started learning some machine learning and statistics, and now I work as a data scientist for Shipt, which is like a gig app for grocery delivery. If you haven't heard of it, you might have heard of Instacart. It's like Instacart. And yeah, I guess I grew up in San Diego. You can see I went to UCSD, lived here most of my life, and then moved away for a little bit, went to various places, and then now I'm back. So really glad to be back in San Diego. And then the picture on the right, that's that's me. I actually, when I was going to school at UCLA, I had several friends who worked at the Large Hadron Collider in Geneva, Switzerland. And over a winter break one year, I went to go visit some of them, and they gave me like a very special private tour through all the tunnels. And so that's the CMS, or compact muon solenoid detector, that they worked on back there, which fortunately usually that area is just like bathed in radiation from all the colliding particles, but they were like kind of taking it apart to fix things up and do upgrades. So very special look into it. So outline for the talk, I guess I'll have like a very quick summary, just kind of prepare you for like, what are the points I want to get across. And then go into 3 other more in detail sections. One is like, what's the evidence that we have for dark matter so far? Like why do we need dark matter at all? Second section is going to be a very brief look into like some of the things that dark matter could potentially be. There's a lot of theories out there as for what dark matter could be, and we don't have a super good idea yet, but I'll go into like some of the more popular theories that we have. And then the final section will be on current experiments that we have to kind of tease out what dark matter could be, and kind of trying to I guess, as you'll see in the second section, there's like hundreds of different things it could be, and we want to kind of pare that list down to the one thing that it actually is. So, so there's plenty of experiments out there, and I'll talk about some of the more popular ones. So very first thing is just super quick. If you don't take anything else away from this this talk, maybe just this slide. Main points I want to get out there is that we don't actually know what dark matter is. We know that it exists. We have fairly overwhelming evidence, and you'll see more of that in later slides. But we have overwhelming evidence that it does exist, but we don't really know what it is exactly. We have like macroscopic properties, or like very large macro scale properties that we understand fairly well, but like the smaller micro scale properties, we don't fully understand. So the things that we do understand are that, one, it's dark. Two, it interacts through gravity. We don't think that it interacts electromagnetically or through any of the other forces, or at least we haven't observed any of that. But it does interact through gravity, which is our main evidence for its existence. And then the other thing is that there's lots of it. So it outweighs regular matter by a ratio of 5-to-1. Right? For every kilogram of regular matter that we have, there's 5 kilograms of dark matter floating out somewhere in the universe. And then I guess kind of going back to the first bullet point, first and third are kind of the same thing. But yeah, we don't really understand what dark matter is yet. Hopefully we will at some point in the future if the experiments that we have going on right now are ones that plan in the future pan out. And because of that, a lot of the ideas that people have for dark matter are hypothetical. So I'll try and take some care to separate, what we do know for sure with what is theory or hypothetical in the future. But let me know if that's not clear. So the evidence so far. So in order to explain the evidence, I guess first I kind of need to describe what properties dark matter has, so that you can see that it can help explain these mysteries that we'll show. So I think, like I said before, it's invisible stuff that only interacts through gravity. We don't see any like direct electromagnetic radiation coming off of it, at least not yet. Some experiments are hoping to look for small trace amounts, and I'll talk about those later. But in the broad sense of things, it's invisible. Can't see it in any electromagnetic band. It also makes up a very, very large fraction of the universe by mass. It's about 25%. And I guess you might do the math in your head and realize, okay, well, if it's 5-to-1 ratio and it makes up 25%, that's only 30% of the universe. And so this other 70% of the universe is something called dark energy. And I should probably note that dark energy and dark matter are two completely different things. And I won't talk about dark energy here at all, but that's also a very large component of the universe's energy content. So those two things are separate, but we'll keep the focus on dark matter. Where is dark matter found? So I guess we think that most galaxies, not all galaxies, but most galaxies have a dark matter halo around them, which is kind of pictured up there in the top right. And so what the halo is, it's kind of like a bubble of dark matter that is like very, very diffuse. It's not nearly as dense as like the regular galaxy that's encapsulated inside. And it extends considerably farther out, like radially than like the rest of the regular matter. So like the Milky Way, for example, I think the disk is supposed to be like 30 kiloparsecs across, and then like the dark matter halo is supposed to be like 120, 150 kiloparsecs across. So it's considerably larger in length scale. It's also cold, and I guess cold doesn't necessarily mean temperature cold in this case, but it means like how quickly it's moving through space. And cold in this sense means that it's moving slowly. So it doesn't free stream between galaxies. Like there isn't, you can't just fly out of the gravitational well of one galaxy and into another one. It kind of stays bound gravitationally to galaxies. And yeah, I guess it's not made out of any known type of matter that we know, and I'll present some evidence for why we think that later. And so we think it has to be something totally new, like a completely new form of matter. So first bit of evidence, I guess both historically and first one I will present, is one of the reasons we need dark matter is to help explain the galactic rotation curves. So when you have a galaxy, and galaxies are made of stars and gas and dust and dark matter, but they're all gravitationally bound together, and the speed with which individual objects in the galaxy orbit that galaxy depends on how much mass is like in the interior of the galaxy. The more mass you have, the stronger the gravitational pull, and the faster things will orbit around that galaxy. And so what scientists noticed a fairly long time ago, I think as early as like the 40s, was that the stars on the periphery of galaxies were rotating considerably faster than you would predict, because if you like look at if you take all the stars that you can see in the galaxy and like add up all of their masses, there's not enough mass to produce the gravitational force that's necessary to get these stars on the outer edges of the galaxy moving as quickly as we observe them to be moving. So that's kind of shown by this green line and red line here in the bottom left. The regular prediction with the stars that we can see is the red, and then the green line is what we observe, and the y-axis is rotational velocity. So we think that there's some kind of missing mass out there that would, if it were present, it would help explain why the galaxies are rotating as quickly as they do. Another kind of related thing is that because this dark matter kind of acts as like a glue that binds the galaxies together, it wasn't just doing its job today in the current universe where we already have galaxies, but it also played an important part in the early universe before galaxies formed. The idea being that because it doesn't interact with itself, it can collapse to form, it can form gravitational wells significantly earlier in time than regular matter would, because when regular matter collapses, it heats up and then rebounds, which kind of prevents structure formation from happening very quickly. And so the presence of dark matter actually is expected to seed the structure of large scale structure of galaxy formation. So somewhat related to the last thing that I mentioned, I guess just saying that it exists is probably not good enough, but we actually have observational evidence for the early structure formation, or how dark matter helped form early structures. And that's coming from the cosmic microwave background. And so the CMB is essentially like a snapshot of what the universe looked like at a point in time called recombination, which was a little over 100,000 years after the Big Bang, I believe. And what it was like before this point in time, the universe was like a very hot plasma, and electrons and protons were kind of just flying around unbound to each other. And then at this point, the universe cooled enough to the point that things slowed down and then started binding together to form stable atoms. And then once the atoms were formed, then the plasma went away, and then light was actually able to move throughout the universe without scattering and being absorbed by the plasma. So that what you see is kind of that's the last visible light that we saw from that moment. And over the eons, it's been stretched due to the expansion of the universe, redshifted. And so now it's it used to be in like the X-ray band, but because of all the expansion, now it's in the microwave band. So I guess the evidence for dark matter here is that if you look at the map in the top left, you can see that there's like hot spots and cold spots. and the characteristic size of those hotspots tell you the size of the gravity wells that formed when things started to collapse to first form galaxies in the early universe. And so if there was no dark matter, you would see that there were I guess larger hotspots, right? If there's more dark matter, there's smaller hotspots because things could collapse more locally. And so the hotspots are expected to be like more frequent and smaller in size. And so this prediction matches very, very well with like the observational evidence that we have from various satellites like WMAP. And then I have a couple of slides on like, some people say like, oh, and why couldn't it just be regular matter, but just dark? Why do we need something completely new? Why does it need to be a new form of matter? So like actually, I guess personal aside, I have a friend of mine who always gives me a hard time. And I think he's joking, but he's always like, Eric, there's no such thing as dark matter. Why can't it just be this, or why can't it just be that? So this is kind of dedicated to him. But so yeah, one potential counter argument is that maybe it is regular matter, but it's just dark. We can't see it. Could it be gas or dust? If the stars, which make up the majority of the mass of visible mass in the universe, those are bright. You can see a star in the sky, but gas and dust doesn't have any light of its own. So what if that was the dark matter and we just had more gas and dust than we expected? And so that's not the case, because we actually can see gas and dust, and it's very, very bright, actually almost too bright in some cases, because in the infrared band, it like almost completely obscures a lot of our telescopes pointing towards the center of the galaxy. So this image on the right, you can see all the swirls, the blue swirls are infrared emissions from gas and dust scattering from other IR radiation that's out in the galaxy. So it's definitely not gas and dust. The second thing maybe is, what if it's like asteroids or planets, small, dark, compact bodies. And I guess if you guys ever studied exoplanets, you probably know that exoplanets are like really, really hard to see because they're small and compact and dark. So what if there's just like a lot of rocky bodies out there floating around in the universe? And so that is also not the case, because there's not enough, I guess, based on the evolution of the chemical makeup of the universe that we understand right now, the materials that you would need in order to form these small compact objects wouldn't be created until stars had already formed. So in the early universe, there's this era called nucleosynthesis, where individual protons and neutrons kind of glued together to form the more heavy molecules, more heavy nuclei. And hydrogen, just a single proton, that's by far the most abundant element out there. But then, kind of going down the periodic table, it becomes less frequent. So there's helium, various isotopes of helium, lithium, beryllium, and so on. And so the heavier elements that planets and asteroids are made out of, like iron and oxygen. I guess the oxygen would mostly be in the form of metal oxides. Those chemicals or elements would not be formed until after stars had already formed and then produced those elements in their cores. So we need dark matter to exist before stars in order to help seed the structure to create stars in the first place. So there's no possible way that dark matter could be made out of these objects because it would be a chicken and the egg problem. And we also know that there's not nearly enough mass. There's no way to produce enough mass to get these asteroids and planetoids in like the right proportions. And then finally, another thing is like, well, I guess the very first bit of evidence that I presented was the galactic rotation curves. And some people have argued that maybe it's not like a new form of matter at all, but maybe it's just that we don't understand gravity as well as we thought. And gravity, the strength of gravity doesn't fall off with distance as quickly as we thought it would. This is a theory called modified Newtonian dynamics, or MOND. And that's, I guess, that theory can explain galaxy rotation curves, but only in like that one specific scenario. And so if you look at it in other situations, it kind of falls flat. So like one counterexample to that is gravitational lensing observations from colliding galaxy clusters. So what we have going on here is you have two galaxy clusters, each with their own dark matter halo. They kind of fall towards each other under gravity and then collide. And in that case, the regular matter, because it has friction and electromagnetic interactions, kind of squishes together, slows down and heats up from pressure, and then the gas and dust from the clusters will radiate in the X-ray. And so that's what you're seeing with the pink overlay in these images. And then the dark matter halos, because they're made of dark matter, they don't interact with each other at all. And so they just pass right through each other. And the gravitational lensing that we can do can trace out like where most of the mass is. And that's what you see in these purple overlays on the images. So dark matter has essentially just like passed right through the galaxy cluster, while the regular matter has like squashed together. And so modified Newtonian dynamics can't predict this kind of thing, because why would the gravity be displaced from where the mass was? It doesn't make sense. So yeah, so that's some pretty serious evidence against that. And then final piece, there is, this is just kind of like a one-off thing, not one of the major things that people cite, but I think maybe some of you may recall a couple of years ago, there was like a story in the news about a galaxy that was found that didn't have any dark matter at all. And so people were like, aha, there is no dark matter because they found a galaxy without it. But actually that's actually even more evidence that dark matter does exist, because dark matter is supposedly like a dynamic thing. Not all galaxies are created with like the same amount of dark matter in them. Some galaxies could have considerably more or considerably less dark matter. That 5-to-1 ratio that I quoted, that's just like a universe average. It could be as high as like 100-to-1 or as small as something less than 1. And so that's essentially what these scientists found here with this dwarf galaxy. They found an example of a galaxy that had considerably less dark matter than regular matter. And so like some explanations for like why that could be the case is, well, it could just be random fluctuations, distribution of the dark matter. It could also be that the halo around the dwarf galaxy was tidally stripped as it orbited the Milky Way, stuff like that. So I guess it's even more evidence that the dark matter does exist. So hopefully I've convinced you that dark matter is a thing. It is real, but like I said before, we still don't really know what it is, right? All the all the evidence that I've given so far has kind of described very, very large macro properties of dark matter, on galactic or cosmological scales. But what does it look like on micro scales? We think it should be a particle or like some conglomerate of particles. So like what kinds of particles could potentially make up dark matter? What kinds of properties would they have? How would they be created? How would they evolve through time? So that is unknown, but there are lots and lots of ideas for what it could be. So this is kind of an image that was popularized maybe about, I think it was 2016 when this came out by Tim Tate from UCLA. And this is kind of like a small cross section of potential different types of dark matter candidates that could be out there. The true dark matter, whatever dark matter actually is, it could be any one of these things. It could be a mixture of some of these things. It might not even be contained within this image at all. It could be something that we still have not thought of. But these are all kind of like more popular candidates. So I'll talk about a couple of like the more popular ones. So the first one, this is like by far the most popular one, is called a weakly interacting massive particle, or a WIMP, kind of a little joke. And it's kind of like your typical particle, because it's more of like a family of particles. There isn't necessarily one theory that predicts WIMPs. It kind of describes like it describes like a set of properties that could be shared by many independent theories. But some of the properties that WIMPs have are, as the name suggests, they're weakly interacting. So they have like very, very small scattering cross sections, and they're also massive. And by massive, I mean like heavy. And so the mass scale of like the typical WIMP, based on theory, is somewhere around 1 TeV, or 1 tera electron volt. I guess just a note about that unit, TeV. So that's a trillion electron volts, and an electron volt is a unit of energy that is required to accelerate an electron through a voltage difference of 1 volt. And because of Einstein, E equals mc squared, mass and energy are equivalent to each other. So physicists like to quote the masses of particles in terms of like their rest energy. To give you a sense of scale, the proton is it's a little less than 1 billion electron volts, or 1 GeV. So this WIMP would be roughly 1,000 times heavier than a proton, or like more. It'd be more massive than like any atom, but like not much more massive. It'd be like I don't know, a couple uranium atoms put together potentially. So that's kind of like that's the most popular one by far. This other one, axions, these ones are kind of cool because they weren't actually proposed to solve dark matter, or like as a dark matter candidate. They were proposed completely independently to solve a different problem with the strong force, called the strong CT problem, that I won't go into. But then it turned out later that these theoretical particles could also be dark matter candidates as well. That they had just the right properties to kind of satisfy some of the observations we have. These ones are kind of very different from WIMPs because they're way, way lighter. So they have masses on the order of about 1 micro electron volt. So that's 1 millionth of an electron volt. And then I guess the WIMP was 1 trillion. So I guess that would be like 1 quadrillion. No, even more. It's like 10 to the 15, 10 to the 18 times lighter than a WIMP. There's also sterile neutrinos. So neutrinos are like a type of matter that we do know exists. These were discovered quite a while ago, and they're kind of like, people typically talk about them as like ghost particles. They're very weakly interacting. They're counterparts to the charged leptons. So like the electron, for example, is a charged lepton. And the electron has a counterpart, which is called the electron neutrino. So there's 3 charged leptons in the standard model: the electron, the mu, and the tau. And the sterile neutrino would essentially be like a 4th neutrino that we haven't discovered yet. And if the theory pans out, the masses of these new sterile neutrinos would be about 1,000 electron volts. So somewhere in between the WIMPs and axions. Some additional ones. So these are ones that like I kind of worked on in my PhD, so I'm a little preferential to them. Cue balls are like an interesting candidate, because they're not a single particle. They're actually like conglomerates of multiple particles that have kind of supercooled and then formed like a large quantum, like a droplet of quantum fluid. And they're very interesting because like some of them can be macroscopic in size. Like you could, I don't know if you could see them directly, but you know, if you could see one, it might, you know, it might be the size of like your fist, or it could be like the size of a house, or it could also be microscopic as well too. So there's like a very wide range of sizes that they could have. They have like very interesting properties. Like some of the ones I studied had like an antimatter reflection property, where like if you took regular matter, threw it at the cue ball, it would bounce back as antimatter. So very weird stuff. This other one, ultralight axions. So that's like the axions that I was talking about on the previous slide, but just like way lighter. And so this has properties similar to cue balls in that they would form a condensate, or like a very, you know, like a blob of dark matter. And that because it's so light, the size of that blob would be like the size of a galaxy or larger. And so the idea is that like the dark matter halos that we see wouldn't be like a cloud of particles. It would be like this blob of quantum fluid that encapsulates the galaxy. So that one's super weird. And then another one, which is kind of gained a lot of popularity recently because of observations from LIGO, as Ken was talking about earlier, is primordial black holes. So these would be black holes that were formed very early in the universe. Typically, you know, standard formation for black holes is to collapse from stars. But in this case, primordial black holes would form from strange inflation models that could form like very, I guess you'd call them like micro black holes. They're still very heavy, but compared to regular black holes, they would be very light. So 10 to the 15 grams is probably about as light as they could be and still survive to the current age of the universe. So those are some of the stuff that I worked on. Weird stuff, but cool stuff. So yeah, like I said, that it could be any one of those 6 things. It could be any one of the 50 things that are on the first slide, or it could be something that we haven't thought of yet. And where the experiments come in is, we have all these candidates. We need to figure out which one it could be, or there could be something that we haven't thought of yet. Maybe an experiment will give us an observation that will make us think like, oh, I never thought of it that way before. So I'll talk about some of the more popular experiments that are out there. You can kind of broadly categorize them into like 3 different types. So I got these 3 diagrams here explaining it, and like the way to interpret it is like particles go in on the left side and then particles come out on the right side. So the flow of time is left to right. In the indirect detection mode, what you have is like dark matter either collides with itself, or I guess in this one you could have like a single dark matter particle that maybe if it's unstable it could decay to other particles. And the hope is that if it annihilates or decays to regular matter, like gamma rays or like electrons or positrons or something like that, then we can detect the annihilation or decay products through regular astronomical observations. So like a signal of dark matter would be like we look into an area of space that doesn't look like it has anything, but then we see gamma rays coming out of that region of space, and that could be an indication that there's dark matter annihilating in that area. The second one would be direct detection, and so these are like more terrestrial experiments where we have, I guess, regular matter as part of our equipment, and then we hope that dark matter would kind of like fly into the experiment from outside, hit the regular matter, or interact with our experiment somehow, and then that interaction would like either shake something or produce radiation, or otherwise create some kind of like observational interaction that we can see and say, okay, yeah, something that we didn't see came in and caused this to happen. The third one would be collider searches, and so these are kind of like the inverse of indirect detection, where we have like streams of very high energy particles, regular matter particles, so like protons, for example, colliding together in order to hopefully with enough energy such that they can produce dark matter if there is some kind of interaction between regular matter and dark matter. And so those are carried out at very high energy particle colliders, kind of like the LHC that I had in my very first slide. So I think I have like 5 or 6 slides here. I guess the first one I'll talk about is ground-based Cherenkov telescopes. So these ones they fall under like the indirect detection branch, and what they're looking for is very high energy particles that like end up coming to Earth. And the idea is that these high energy particles were created by dark matter somewhere out in space, either through annihilations or decays. And the way that they work is that, I guess there's 2 different kinds in here. One detects gamma rays, and then the other one detects neutrinos. And the way the gamma ray ones work is that the gamma ray enters Earth's atmosphere, it strikes a nucleus, and then causes that nucleus to essentially like blow up, and then create an avalanche of radiation and like other high energy particles that kind of all interact with each other to produce a very bright flash in the air. And the hope is that by observing these flashes, we'll be able to reconstruct like where the gamma ray came from and what energy it has, stuff like that, and then that information can be useful for trying to like fit a dark matter model. So like I guess the image that I have on the very far left, Hawk, and the one on the very far right, CTA, which is this Cherenkov telescope array, those two are looking for gamma rays specifically. And then the ones that are looking for neutrinos, that would be IceCube up in the top right, and then the Super Kamiokande in the middle. Those ones operate in a similar manner, but they're like deep underground. And so they can't see these air showers from gamma rays. And what they're hoping is that like a very high energy neutrino will come in from space, go through the ground and then interact with like the material of the experiment. So like Super K is like in a mine deep underground. Ice Cube is very, very deep below the Antarctic ice. And so the reason they do that is because they don't want a lot of like background signal coming from other particles. They want to be very sure that whatever they see in the experiment is like almost certainly a neutrino that that came from space. So those are kind of ground-based telescopes. We also have space-based telescopes as well. So these ones come in a couple different flavors. There's like gamma and X-ray telescopes, kind of the counterparts of the gamma and X-ray telescopes from the previous slide, except these ones don't detect air showers because there's no air in space, but they directly detect the gamma rays and X-rays themselves. So that would be like Fermi-Lat, the one up in the top right. There are ones that detect cosmic rays. So by cosmic rays, I mean like any high energy particle that isn't electromagnetic in nature. So that could be antimatter like positrons, antiprotons, anti-helium nuclei. It can also detect regular charged particles like electrons. And I think it can also detect neutrons as well, but I'm not 100% sure on that. And that's the biggest one falling under that would be the AMS, or alpha magnetic spectrometer. And that it doesn't look like a regular telescope. It's kind of just like a box that sits on the International Space Station, and then just kind of passively sits there as particles fly through. And then I guess the third one would be observations in the visible and infrared. So that would be like your typical telescopes that you would use to do things like exoplanet research and deep field imaging. That'd be like Kepler, the new James Webb telescope, and Hubble. And so these ones, I guess, aren't super helpful in like seeing decay products, because a lot of the decay products from annihilating dark matter are expected to be like very high energy, so like out of the band that the visible telescopes can see. But they are useful for gravitational lensing experiments. And so the gravitational lensing, where that can come in, is like it's particularly relevant for black holes. So like if primordial black holes were dark matter, we would expect light to bend around the black hole because of the gravitational pull. Same thing for like subhalos of dark matter too. So it's not specific to black holes necessarily, but black holes is probably like the most popular candidate that would be detectable via this method. And so the idea is that for these compact objects, if one of these objects passes between Earth and like a star in the background, you'll see a temporary increase in brightness from that star, because now you're not seeing light from just from a straight path from the star to Earth. You're seeing light from like multiple paths that would normally just miss Earth entirely, but are now being focused back towards Earth. And so you see a temporary bit of brightness that could last anywhere from hours to days, and you can kind of like reverse the process mathematically to figure out what the mass is of the object that's doing the lensing. So the visible telescopes can help out with this. And then as for direct detection, So some of the more popular experiments in this branch are what's known as like liquid noble gas detectors. And so the way that these work is that, well, I guess as the name implies, is that they're basically just like buckets that are filled with supercooled noble gases. Specifically, I think xenon is like the most popular one to use for various reasons. Like you can have it written down here. Oh yeah, it has no natural radioisotopes, right? So it provides like a very clear signal. There's no background from like decaying regular matter. But the idea is you have this bucket of very cold liquid gas, and the hope is that dark matter will fly into this bucket from outer space and hit something inside, and then when it does hit one of the nuclei, that will cause a kind of a cascade of radiation, very similar to the air shower, the gamma ray air shower that I described before. But now it's not happening in the air; it's happening in liquid xenon, and so that that'll cause like a flash that should be visible by detectors that are inside the bucket. Those are those. I guess if you look in the diagram on the far left, you can see it says like PMTs on the top here. That stands for photomultiplier tubes. So they're basically just like cameras that very, very sensitive cameras that if you get a single photon in there, it causes like a chain reaction, which then produces a signal. So these are yeah, very, very, very sensitive experiments, and they typically need to be very far underground. So like, I don't know how far underground this Gran Sasso one is, the one in the middle. I think it's under a mountain in Italy. But I know the one on the right, the Lux Zeppelin one, that's in like a formerly abandoned mine in South Dakota. So they kind of dug it out and dusted it off and brought their experiment down there because there shouldn't be any background radiation from like other regular particles coming in from the surface. And then I guess in addition, more indirect detection. So I guess these liquid noble gas detectors are primarily useful for detecting WIMPs, the weakly interacting massive particles that I mentioned before. Axions, because they're so much lighter than WIMPs, require like specialized experiments to detect them. And so they, I guess the types of experiments are called like haloscopes. And resonant cavities. And the way they work is that the axion it's theorized to have like a very, very small interaction with light. And so if you have an axion that's in a very, very strong magnetic field, it could spontaneously convert from an axion to a photon. And so the idea with these resonant cavities is you have like a really strong magnetic field in the cavity, and then any axions that might pass through could potentially convert to photons, and then you'll be able to pick up the signal from like the resonating radio wave that's inside the cavity. So there's plenty of these things at various places all over the world. They, like the other indirect detection experiments, they also need to be like super cooled in like a cryogenic cavity. And then finally, I think this is my last slide on experiments, but the final type of experiment would be particle colliders. And so I guess as I mentioned before, the way these work is that you get some regular particles And the types of particles that are used depends on the accelerator itself. So like the Large Hadron Collider in Switzerland, that one uses proton-proton collisions. But you can also, I guess there was another accelerator in the United States that got decommissioned a couple decades ago called the Tevatron Fermilab, that used proton anti-proton collisions. And then there's various other colliders that collide like electrons on electrons or electrons on positrons. So the types of particles that you collide are different in different colliders. But the goal of all of them is the same. We want to collide these particles with very, very high energy, hopefully enough energy that we can produce new particles out of the ones that we're colliding with all the additional energy that we're injecting into the system. And some of these new particles could be dark matter. And so like one problem with this is that if your collisions produce dark matter, and we know that dark matter is dark and it doesn't really interact with anything, how do we observe that it was actually produced? So the way that that's done is we look for I guess like partner particles in the collision that were produced at the same time but have opposite momentums. So you've probably heard of conservation of energy and conservation of momentum as like laws of physics. And so we use the conservation of momentum here to tell us, okay, well, we saw these two particles going in head on, and then like one or two particles came out on this side of the collision, but we didn't see anything coming out on the other side. So by using deduction and the law of conservation of momentum, you can infer that there were in fact other particles that came out the other side of the collision away from the ones that you could see. And so you can reconstruct the collisions in that manner. And so yeah, there's a bunch of different experiments that are doing these all over the world. I've got the LHC on the far right. That one's typical proton-proton. This one in the middle is kind of a special mention. This one's specifically looking for axions because of the magnetic field effect that I mentioned on one of the previous slides. Basically what they're doing is they're shining a laser at a wall, and the laser and wall are in a very strong magnetic field. And so they're hoping that some of the light from the laser will convert into an axion, pass through the wall, and then convert back into photons. And then there will be a camera on the other side that'll be able to pick up the light as it transmutes back and forth between axions. So that's kind of a very, very interesting experiment, but not typical. And then the one on the far left, that's the heavy photon search. This one's also a little different in the sense that it's not colliding like two beams of particles, but it's got a fixed target, which is made of tungsten. And then they accelerate electrons towards the fixed target. And then with enough energy that it should produce certain types of dark matter. I think they're looking for something called the dark photon. And actually, one of my friends that was on like my very first slide, he's now a postdoc that works on that experiment. So yeah, those are some of like the more popular experiments. I guess this is my final slide, so I'll just kind of sum things up. Like I showed you, there's lots and lots of different ideas for what dark matter could be. We know that something that satisfies the properties of dark matter has to exist, but we don't really understand exactly what yet. There are lots of experiments to try and figure out, as you saw from the various slides that I had. But I guess it's considerably easier to like make up new ideas than it is to test them. So one problem the field has is that there's so many ideas and then not enough time or energy or money to devise the experiments to test all of them. So that's one potential problem. And then one thing that I didn't talk about, but is kind of gaining traction, is computer simulations. Because you can't observe like galaxies evolving in real time. You can't see them collide in real time. People have turned to numerical computer simulations to try and figure out like, okay, well, if we have dark matter with like certain properties, what would we expect to see if like two galaxies that had dark matter halos collided together? And then we can use the information from those simulations to help us look for like small deviations in like the dark matter distributions that we see due to gravitational lensing, for example. So that's like one thing you can simulate with computers. It can also help with like formation simulations as well too. So like when I say formation, I mean like formation of the dark matter itself, because usually these theories are like dark matter is created in the very early universe, which is something that we can't observe directly because it happened so long ago, and there are observational issues with seeing things that happened very, very early in the universe. So simulating some of the things that happened in the very early universe is like another potential avenue for investigation. And yes, I guess that's all I have. Thank you for listening to me ramble, and if you guys have any questions, I'd be happy to take them.
Well, thank you. That was a very interesting talk. Any questions?
Yeah, Eric, this sounds like the hunt for the Higgs boson type of thing that's going to go on for years and years and years until we kind of capture what the stuff might be.
Yeah, definitely. I guess the Higgs kind of like eluded physicists for the better part of 50 years. I think it was originally proposed in like the 60s or early 70s, and then we didn't end up discovering it until 2012. So yeah, it kind of eluded us for a while. And dark matter is kind of in the same area where like we know that something like it exists out there. We just don't know exactly whether it'll be discovered with colliders like the Higgs was. That's an unknown question. It could be, astronomical observations might be the key to figuring out what it is too. So we try and diversify our experiments to keep our options open.
John Bachman asked a question. Have any of the experiments seen what could be a dark matter signal so far?
That's a good question. So there are hints of signals. There isn't a smoking gun from any of them, but there are all sorts of like little things that kind of cropped up that people are like, oh, this is interesting, let's look at that. Some examples I can give you off the top of my head are when they first turned on LIGO, for example, they saw that the typical masses of black holes that were colliding were considerably larger than regular astrophysical black holes. Their masses were on the order of like 40 or 50 solar masses, but regular black holes that would form from collapse of a star, those are expected to only have masses of like 1, 2, 3 solar masses. So these like very large black holes kind of made people think like, oh, maybe these are primordial black holes and they were created much larger regular black holes. So that could be one example. There's also something called the Fermi excess. Let's see if I can go back. So this satellite that I showed a picture of, Fermilat here, it I don't remember when this happened, but it observed like an excess of not gravitational. It observed an excess of gamma rays that was coming from the center of the galaxy, and it wasn't a significant excess, but it was like, you know, just enough excess gamma rays to make people curious as to, like, you know, what could be causing that. And the idea was that, you know, if there's dark matter in the center of the galaxy, which by, you know, according to theory, that would be where the dark matter would be the densest. If it were annihilating in that region, then it would produce gamma rays, and then maybe that's what we were seeing there. So there's hints there. But one other one I can think of, I forget the name of the experiment. Remember, it started with an A, but there was one that was looking at, it was a direct detection experiment. So one of these types here with the liquid xenon. Not any one of the two that I'm showing here. I forget the name of it, but it observed a seasonal modulation in like its background signal, and so people thought that that might have been due to the fact that, like, you know, the Earth is going around the sun, and there's this stream of dark matter. They call it the dark matter wind that we expect to be, you know, moving through our solar system. And so, you know, at one time of the year, we're moving with the wind and detecting less particles. And then at another part of the year, we're moving against the wind, detecting more particles because of the higher flux. So I don't think of that one. There's a lot of controversy around that one, whether they actually saw a signal or not. But there, yeah, so I guess to answer your question, there have been hints, but nothing for sure so far.
Let me ask one, and this is going to be a confused question. At the end of recombination, or at the beginning of recombination, where we're getting star formation, the model always is there's a generally homogeneous material, dark matter and regular matter. Most of the regular matter is hydrogen, but there's just small variations in primarily dark matter, I believe, that will lead to gravity wells and concentrations of enough now regular matter, which would be hydrogen, to begin to form stars. How clear is that kind of an explanation, given all the different possibilities for what dark matter might actually be physically? Or is there something special about dark matter, for example, if, you know, much heavier than individual protons, so maybe two little dark matter particles could begin the gravity well to draw in more hydrogen?
Oh, I think I see what you're asking.
You see where I'm
like,
going?
Yeah, why does dark matter collapse differently from regular matter?
Yeah, what's special about dark matter, given that we don't know exactly what it is?
Yeah.
The explanation is always it's the dark matter that causes it, causes this phenomenon initially.
Yeah, so the property that makes dark matter different in this regard is like the lack of pressure amongst dark matter. So like if you think of, I guess if you think of like the primordial plasma as a gas and dark matter as a gas as well, because dark matter doesn't have any self interactions, it also doesn't have any pressure. It's like a completely non-interacting gas, and so any small instabilities that form will have like a runaway effect. There's no way for there's no restoring force that, like, you know, if you were to get an overdensity in this region, it wouldn't like spread back out. But with the plasma, it does have pressure, And so if you had some region where the plasma got more dense than other regions, there's a tendency for it to spread back out if it's not so dense that it will collapse gravitationally. So there's kind of I guess a barrier to formation for the plasma that the dark matter does not have. And so it collapses gravitationally much earlier than the regular matter.
Thank you.
Yeah.
We have a question from Nate. He's asking, what would we gain from discovering what dark matter is actually made up of? Assuming it's made up of something we already know exists.
Assuming it's made up of something we already know exists. You mean like some of the slides I was sharing earlier that says like it's not made of something that we know exists? Do you think you could clarify?
Nate, feel free to unmute and ask the question.
Well, I guess I can answer the first part of the question. What do we gain from discovering dark matter? Hard to say, right? I guess with any scientific discovery of like this more, it's more on like the frontiers of knowledge kind of area. With those kinds of discoveries, it's always hard to say like what practical outcomes you can get from it. I'll give, like, for example, the invention of a laser. When people first invented the laser, it was just that they had no practical application in mind. It was just like, oh, hey, we found a way to create coherent light sources, and it was just it was just kind of like a lab trick for the longest time. And then eventually somebody realized that you could use it to send information and like etch materials and like read and write from CDs. And so it kind of like developed all of these practical applications later on that were unforeseen at the beginning. It might be more difficult to commercialize dark matter because, like, from what we know of it so far, it doesn't interact with regular matter, so it could prove very, very difficult to control. But I guess until we figure out what it is exactly, it's hard to say for sure what kind of practical applications could come out of its discovery.
Annette Brown asked a question. What common elements, if any, does dark matter and dark energy have? Is it a commonality?
Yeah, that's a good question. I guess the name is probably the biggest one. So yeah, obviously they both have the word dark in there, meaning that we can't readily see it. I guess I can talk a bit more about dark energy. Supposedly, what dark energy is that it's like a uniform energy source that permeates the universe. And it has the special property that it does not get diluted with the expansion of the universe. So that's very special because, like, with most regular energy sources in the universe, they do get diluted as the universe expands. So like matter gets spread out. Radiation gets double penalized, actually, like photons, because it gets spread out, and the wavelengths also get stretched, so it loses energy in more ways than one. But dark energy is very special because it does not get diluted. So it's honestly it's even more perplexing to me than dark matter. At least with dark matter, you can see like clumps of it. Get gravitational lenses and whatnot. Dark energy so far, there isn't like a region of space that we can point to and say like, oh, here the dark energy is located here. We just know that that like due to the expansion properties of the universe, that something like dark energy probably exists. So in that sense, it's kind of similar to dark matter. It's like we don't know what this stuff is, but according to our current theories, if something existed with the right properties, then it would explain our observations. So yeah, so those are kind of the ways in which they are similar, but they may or may not be related.
James Brunton asked, could you comment on how the negative results from the experiments have affected our theories?
That's a good question. So there's, I guess, definitely some theories have been ruled out, or at least certain regions of parameter space. So I don't have any plots here and to show you, but I guess most of these experiments, they're the way they like present their results is they'll have like a two-dimensional plot that's like that plots like one characteristic of dark matter on one axis and then like another characteristic of the dark matter on the other axis. Usually it's something like the interaction strength and the mass, and so different experiments are sensitive to like different regions of that parameter space, and some of the experiments have already started to exclude like wide swaths of some of that parameter space. Actually, the direct detection ones involving the liquid xenon, these ones have actually almost entirely excluded the parameter space that we expect to be observable. There's something called the neutrino floor, which I won't get into, but they basically almost entirely excluded the experimentally probable parameter space. So you can rule out certain dark matter candidates. Oh, and I know for axions, one of the things I mentioned, here in this slide. So the axions, there's actually several different like flavors of axions, or there's like there are different theories that can produce particles that are like axions. And there's one called the QCD axion, and that one I know that one has for sure has been ruled out. So some of the other ones, they're still alive and moving along, but that QCD axion has been ruled out. So it is testable.
Let me ask a morphology question. You said that galaxies would have these very large halos of dark matter surrounding them. Would the structure of the halo, I'm thinking, mentally a spherical thing, but would the structure of the halo depend on the morphology of the galaxy itself? I mean, would they be elongated, or would they have a corresponding shape?
Yeah, so I guess the morphology isn't my forte, but from what I understand, they are not expected to be perfectly spherical. Like you said, they're phrase I've heard is like triaxial ellipsoids. That's kind of what they're expected to be. It's very fancy word, but it just means that it's like you take an ellipse and then like rotate it around an axis, and that's the volume that it looks like. So it could it could look more sphere-like. It could look more like an elongated, like a pill or something. You'd like take for medicine. So those are like common shapes that we expect them to be in. And you actually can, to some degree, or hypothetically, you can test the morphological structure of these in certain theories, like the dark matter annihilation scenario that I mentioned, with like that could potentially be observable by the Fermi-Lat telescope. So like depending on the shape of the halo, you can kind of like trace out the profile of the halo according to the gamma ray emissions. So like you would expect to see more gamma rays coming from areas where it's denser and less gamma rays from areas where it's not as dense. And so in theory, you could reconstruct the shape of the halo, at least in that small region, and get like a density profile. There's also these the potential for these subhalos here, which I probably should have mentioned. I don't think I did. But subhalos are like smaller regions where the dark matter has kind of formed more compact structures, and some of these subhalos you could potentially see with gravitational lensing experiments, like I explained here. Yeah, so you could have like subhalos floating around within like the overall halo, and you would expect that they would be more numerous towards the center of the galaxy and less numerous towards the periphery of the galaxy. And so you can kind of get an idea of the distribution there if these kinds of things were observed. This is another example where it's someone saw like someone saw a lensing event that may or may not have been an indicator, but we're not 100% sure because it was just a single event. It's another near hit.
So there's not a systematic search for this through gravitational microlensing.
Yeah, there's several experiments that are looking for it. I guess if you see this this plot on the left-hand side, the Eros Macho experiment was one that ran, I think it was like almost a decade ago, and that's the one that saw the one candidate event that everybody talks about. And then Kepler and HSC. HSC is like a submodule in the Subaru telescope in Hawaii. But these are ones that are like more recent, and they're currently accumulating data to try and rule out regions of parameter space here.
Dylan asks, is it possible that dark matter is just empty space? Question mark. Maybe some kind of pressure between large bodies of matter?
So that, I guess that's a good description of dark energy, potentially. I guess we don't know whether, what dark energy looks like on smaller scales, but I have heard some theories of dark energy that that work like that, where like the mass kind of acts as like a screening force that like pushes the dark energy away, and so dark energy would only exist in like the empty space between massive bodies. But I guess that's not something that that would describe dark matter, because dark matter is kind of the opposite, right? It's a tracer of mass, because we expect them to interact gravitationally. So like where you find regular matter, you would also expect to find dark matter, because they're gravitationally attracted to each other. Hope that answered the question.
Yes. Any other questions?
There is one more from Dennis Amon. Yeah.
I knew you were going to do it.
Yeah, Eric, did your parents help you with science projects in primary school? And did you leave your fellow students in the stardust?
Let's see. Well, so my dad is an engineer, so he definitely helped me out with like some math related stuff early on. But I guess at some point I ended up outpacing him, I believe. But yeah, parents definitely did kind of encourage my studies when I was younger. Actually got in trouble a lot because I would read in class, not listen to the teacher.
I'm kind of curious just exactly how you got into the study and science of dark matter. That's kind of, a very narrow little niche of astrophysics and all that fun stuff. What took you there?
Yeah, it's kind of an interesting story because I kind of fell into it. I didn't realize that was what I wanted to do. I suppose when I first started grad school, I mean, I guess from an earlier age, I know I wanted to like study physics. And then as I grew older, I kind of gravitated towards like the more like theoretical things like elementary particles and string theory. And I thought that, oh, I want to be a string theorist because it's super tough stuff. And it is super tough stuff. I did take a couple classes on it, and it is very, very difficult. But I guess the thing that kind of drew me to this was in our first year of grad school, they have like they have a class which is basically where all the different professors come and they give lectures on their research to kind of advertise to the students what kind of research avenues are available. And the professor that would eventually become my advisor, he came and gave a talk on his work, which was researching dark matter. And the thing that really changed my mind about it was that it's the astroparticle physics studies everything from like the smallest subatomic scales all the way to the largest cosmological universe scales, and even in some cases larger than the observable universe. And that was kind of the thing that really blew me away. It was like, with this one field, you get to learn everything on, I mean, not everything, but I mean, you get to learn about things that exist on like very, very wide ranging scales. And it was very cool that you could like learn, you could use ideas from particle physics to help you solve problems in cosmology. So I think that was the thing that made me really interested in it.
Given your presentation here, do you have is there one experiment or that you have an opinion on that'll prove more effective than the others that you've shown in here? Because you've shown several different ways we might detect it. Do you have a favorite or something you think is going to be more successful than the others?
Good question.
That's really tough.
Because if it comes down to a matter of what is going to get funded first, because I can't imagine that everybody's going to throw different money in different directions, being that this is a fairly narrow field of experimentation. Where do you think the coin ought to go if you're going to make success out of it?
That is a very tough question. I guess, if I was being selfish, I'd say like these kinds of experiments looking for signals from gravitational lenses, particularly because like I used to study black holes. So that would be like my selfish answer. I guess from the financial perspective, where should the money go? There have been some interesting experiments in the particle collider space that are relatively cheap. So like the heavy photon search, for example, this is like I guess there's like a human here for scale, but like this thing that you're looking at right here, this is only like a meter or two across. So it's like a very small experiment. It still requires a particle accelerator, but you can build the detector apparatus for $2 million. And so that's considerably cheaper than like some of these massive particle accelerators like the Large Hadron Collider, which cost several tens of billions of dollars to construct, and then there's like ongoing maintenance and stuff. So some of these smaller experiments are definitely more more like financially efficient, I guess you could say. These like Axion haloscopes, those are also relatively cheap to produce as well. You can probably build one of these less than $1 million. These ones are probably more expensive because they're very large in comparison to the haloscopes, but I don't know, maybe a couple tens of millions of dollars. And then these ones are bigger too. The Super K, you have to like excavate out. For a lot of these experiments, like the reason they choose abandoned mines is because like excavating the material out is like one of the more expensive parts of the of constructing the experiment. So these ones are pretty pricey too.
Some of these are dedicated more or less to the search for dark matter, but is there a symbiotic investment? Suppose somebody built yet another big, a larger collider that along the way would help you perform experiments that would begin to answer these questions.
Yeah, there's definitely like some overlap between the search for dark matter and like other areas of physics that people are interested in as well. So I think I don't know if you could like rank these experiments from like least overlap to most. I'd say probably the Axion haloscopes these are like specifically tuned for dark matter and not useful for much else. But then other experiments like these particle colliders, they're not necessarily just looking for dark matter to be produced. They're looking for all sorts of like beyond the standard model theories or evidence of some of these BSM theories. So like things like supersymmetry, for example, strangelets, just like all sorts of interesting things that are could be completely unrelated to dark matter. You can use these to investigate those kinds of theories. Same thing with these Cherenkov telescopes. So like because they're not designed to directly detect dark matter, they're just looking for like gamma rays and neutrinos and stuff. There are other astrophysical processes out in space that produce gamma rays and neutrinos that we would be interested in. So like, for example, I know Super K has done experiments, or well, I guess there's been analysis done on the data collected at Super K that looks at neutrinos coming from the sun, and then as they pass through the Earth, they kind of transmute themselves from like neutrinos of one type into neutrinos of another type. And so by measuring the relative fractions of those, you can help determine like what's the propensity for them to transmute, and then also like what their masses are, because that's like another unanswered question in physics, which is we have these 3 neutrinos and we don't know what their masses are. They're so light that they kind of like evade direct measurement of their mass, so we have to use indirect methods to figure out what their masses are. So that would be like a great example of 2 completely different fields of physics that are using the same experiment to answer different questions.
Are there any more questions? You can tell how popular your talk was because you've gotten, almost 40 minutes worth of questions.
I'm kind of curious where the major source of funding for this research comes from.
Yeah, that's a good question. I guess it depends on the type of experiment and like where it's located, I suppose. So like obviously some of the ones that are like part of a pre-existing international collaboration, like the LHC, for example, and that's in Switzerland, that gets a lot of its funding from the European Union itself, because it's like it's not a national lab, but it's kind of like, you know, the equivalent of a national lab in the EU. So that gets a lot of funding from there. But then it also, because it's an international collaboration, they also get funding from like the member nations as well. So that one's kind of like a mixture of different funding agencies from all over the world. Other ones like, let's see, like some of these ones, for example, are probably, you know, this is something that you could build in a lab with like, you know, one professor and maybe like 3 or 4 grad students. So it doesn't require as large of like an international collaboration necessarily. And so the funding sources for that are probably more local and would come from you know, maybe one or 2 grants. So like maybe there's, you know, one professor or 2 or 3 professors that are working on one of these experiments, and so they'll write grants to like the funding agencies that they typically ask for funding. So that could be, you know, government funds, like the Department of Energy, I know is one that funds a lot of these experiments. What's it called? The National, the name evades me, but there's another U.S. government funding agency that provides a decent amount of
The
funding.
National Science Foundation.
Yes, yeah, NSF. That's what I was thinking of. Yeah, the NSF. That and the DOE are probably the 2 big ones in the U.S. And for, you know, more for other experiments that are, you know, done in other countries, like this organ one in Australia, I imagine they probably get funding directly from the government of Australia.
Yeah.
There was a very interesting, I think it was a NOVA program on the hunt for the Higgs, and they touched a little bit about the funding of how it happened. I'm pretty sure it ended up, the discovery happened at the LHC, but even so, you kind of think, all right, so from 1964 through 2012, the funding necessary to go find something that that was obviously important to set, to come up with how energy is created or stored. It's, again, you kind of look at the search for dark energy and dark matter and going, okay, so, the science is interesting. The science is probably very important, but it's not exactly on top of anybody's hit list. So it's kind of like, okay, who throws out the coin for that? But thanks for the background.
Yeah, it's that kind of goes back to like my comment on like lasers, and like, you don't always know what the practical applications of certain things are. If I could expound a bit more on that, there's also an alternative dimension to like practical effects, which is that, maybe you don't discover, or maybe you don't find like a practical application for the Higgs boson itself, but maybe you do find practical application for like the experimental technology that you devised in order to search for it. So I know one of my friends is like very vocal and always saying that like a lot of the advances in cancer therapy that have come out over the last couple of decades are due in large part to like accelerator technology that is being pioneered by experiments like these. So like I don't have any examples in these slides, but there are fields of research which are trying to like make accelerators on a chip. So like when you think of an accelerator, you probably think of like, there's like a very big facility that's miles long, and you need to launch electrons through a cavity in order to get them up to speed. But there's been like a lot of really cool breakthroughs recently in accelerator technology to make them like smaller and more compact. I have a friend that I know from UCLA, and he's a postdoc at SDAA now. And he's working on something called plasma wake field accelerators. They're, I guess I won't explain what they are, but it's basically like a way to accelerate electrons up to energies of a billion electron volts that on a tabletop experiment that's like less than a meter long. So you can create these accelerators that are very small and like very focused. And I don't think electrons are useful for cancer therapy, but I know like advances in proton radiation therapy have had like a great practical effect. You know, you like blast a tumor with like very precise beams of protons, or or another medical procedure that utilizes accelerators would be like a gamma knife, for example, where they shoot gamma rays to destroy a tumor, that are built using I guess the gamma rays are produced using a particle accelerator. So there are indirect effects that don't come directly from the discovery of this new particle itself, but like all the technology that you use in order to figure out in order to make the discovery, I guess. And that provides some like additional value.
Anyone else?
I mean, we can go on forever, but let me pose a kind of a final, deep philosophical question. There are all these big questions: dark matter, dark energy, the grand unified theory. How does, quantum mechanics work with general relativity, and all of these things that are really tough nuts to crack. But do you think there's, like if you solve some specific issue here, then it breaks the whole thing open and it's understandable? Or are we always going to be pecking at one more imponderable kind of conundrum that in reality only a very small part of the population ever really understands?
Yeah, that's a good question too.
If we solve dark matter, we don't solve it all?
Yeah, I think dark matter, probably, like if we solve dark matter, it might be a dead end from the perspective you're looking at. Like, maybe we figure out what dark matter is, but it might not. It might just be like some other particle in like a pantheon of like dozens of other particles. It could be like uninteresting from like a deeper philosophical perspective. One thing that I think would solve like a lot of problems, and then probably even produce like new questions that we haven't even thought of, would be the unification of gravity in quantum mechanics.
Yeah.
Because right now it's like completely unknown how to combine them in a way that's like self-consistent and produces nonsensical results. There's some ideas. I guess primarily string theory is one that or one candidate for such a unification. There's a couple others out there too. I think being able to answer that question would probably open up like whole new vistas of ideas and questions that we hadn't thought of.
Yeah. Well, listen, thank you so much for the presentation. I know you contacted me and offered absolutely phenomenal session tonight. Thank you again. And for all those who are still here, remember the event on Friday. Come early if you can. 6 o'clock will be the presentation by the council member.
Cool. Yeah, thanks again, everyone, for having me. Have a great day.
No, seriously, this is wonderful.
Great talk.
We're going to terminate the meeting and see you on Friday or at the next program meeting, Star Party, whatever.
Thank you. It's a great talk.